Hey, what's up, guys? So this is my video about the back theory, measure theory. Yeah, so to previously I already introduced the additive and countably additive, and basically talk about what is the sigma ring. So in this video, I want to give you the exact and the construction of the Lebesgue measure. But basically, I will prove the main theorem in the measure theory by basically tell you how to construct the exact Lebesgue measure. Also, this video may be very long, and I hope you guys subscribe to my channel. Okay, so my construction is RP is a p-dimensional Euclidean space. Okay, and I think everyone knows about interval, right? So let me define an interval. So interval in RP is defined to be, let's say, a collection of a set, which x, they can be written as, let's say, x1 and x2, and x1 to x, let's say p, and each xi squared, that's equal to bi and ai. Okay, collection of everything. Okay, so this is called interval, and then you can replace this greater or equal to be greater or less, or one of its. So basically, you have 4 choices, and the collection of everything of these are called interval. Okay. Okay, so if A is a union of finite intervals, then A is said to be an elementary set. Okay, so elementary, what is the elementary set? The elementary set defined to be a finite union of the open or closed interval, right? So in one dimension, maybe these are a collection of these two are union of these two are elementary set. Okay, so for this interval, let's say I is an interval, I define a volume to be I from 1 to n, or the measure to be bi minus ai, I from 1 to p. So it's the standard volume. Okay. And let me define this epsilon to be a family of all elementary subset. So epsilon is all elementary subset. In RP. Okay. Okay, so your exercise is very simple to check that epsilon is a sigma is a ring, but not sigma ring. Okay, and you can check that this M is additive. Okay, so this is just the simple definition for find a measure on the intervals or the elementary set. Okay, so the idea is that the construction of such thing one can try to generalize. Okay, so let me just give you another definition. So let's say, so phi is a non-negative. Let's say phi is a set function which is non-negative, and the non-negative set function, and we call them regular. Sorry, we call the phi regular, means that let's say on the outer elementary set, means that for every a belongs to this elementary set, and for every epsilon bad notation greater than 0, there exists the f, which is closed, and the G is open, such that A is covered by G and cover F, and phi, right? So phi of A is less or equal to phi of F plus epsilon, less or equal to phi of G minus epsilon. Okay, so what this means is that given A, right, you can find G and F such their volume are so close, right? If you view phi as a volume, Okay, so very simple. Also, a very simple exercise is to check that M is irregular. Okay, so now we can go to prove the main theorem. Okay, so let me just write down main theorem. Okay, so so let me just write down idea. So the idea is that the idea is that suppose you define mu, you can define mu. Sorry, the main theorem idea is that you can define mu on elementary set, which this measure on elementary set should have some better properties. And once you have that, you can try to generalize. You can try to define so-called converge, and you can make a large set which are measurable based on once you define an elementary set. Okay, so in order to do this, we need to introduce the outer measure. So definition, let's say mu is so now I give 4 conditions for mu. Okay, so this mu should have first condition is that additive means that the mu of A union B will be mu of A plus mu of B if they are if their intersection are trivial. Okay, the second is non-negative, which is mu of A is greater or equal to 0. And the third is finite. The fourth is the regular. Okay, so basically, let's suppose mu has, so let's say mu have 1, 2, 3, 4 on elementary set. The same reason elementary set. Now I can define a so-called outer measure. Okay, so the definition is that as let's say given any E in RP, right, in a P dimension, I can find suppose I can find a lot of countable union of a set which is in an elementary set, so such that the E is countable like this, and each AN belongs to the elementary set, and I can define the outer measure of this E defined to be the infiniment of, right, so this AN is elementary set, right? Elementary set is countable, the countable union of intervals, right? So I can define so I can compute each AN, right? Because now mu is only defined on an elementary set. I take N and I take an infiniment. Yeah, so this is an outer measure, so-called outer measure. Okay, so to the trivial property is that if E is a subset of E1, E is a subset of E2, then the outer measure by definition is less or equal to mu star E2. And the second is that since mu is non-negative, right? So outer measure should be non-negative. It's all just the property of inf. Okay, so this is outer measure. So let's give two important theorem of outer measure. Okay, so the first theorem should be very intuitive. If A is in an elementary set, then the outer measure of the A should be the same as our measure. Because we want to start from the measure of the elementary set and extend it to the outer measure. Okay, so and the B is that if E is a union of the outer measure, then which it has a sub-activity basically is this. Okay, this is called a sub-activity. Okay, so let's give the proof. So remember that we are not just dealing with the Lebesgue measure. We are dealing with any measure which has the 4 properties on an elementary set. Oh, sorry. So the elementary set is divided with finite union, right? So this is why this finite is important, because if mu is unfinite on some intervals, then it should be finite. By definition, I require it should be finite on all the finite collection of them. Okay, so A is trivial. Let's say A belongs to an elementary set, and choose small epsilon to be greater than 0. And so we know that. So okay, so let's start, right? So by definition, A is in an elementary set, right? So A can cover itself. And so A can cover itself, which tell you that mu star A should be less or equal to mu of A, right? Because mu star A is inf. Okay, so this is the first directions. Okay, so the property of mu star A is infiniment, right? So that means there is this sequence of an such that there exists an such that A is U covered by an, and the mu star an, right, by definition is infiniment, right? So if you take mu star, there must be some small tiny difference, which you have this. Right, this is due to the inf, right, the inf property. Okay, and now we can use we can use the property of mu to be regular. So regular means that what A contains, right? So now A is regular. I mean mu is regular, right? So A contains a closed elementary set. So A contains a closed elementary set. Okay, closed elementary set, right? By definition, there is a F which is a closed elementary set F, such that F is A1 union A2 is AN. The reason is that this is closed elementary set, and so F is compact, right? So you can find finite of them. So you get your mu of A. By property of this is right, by property is non-negative, right? So mu of A will lesser and regular. So regular tell you that mu of A plus mu of F plus F lesser plus epsilon, right? And then this is lesser equal to mu A1 union of up to AN. And by property of this mu, I know that is summation of mu AN, and from 1 to n plus epsilon, which is less or equal to mu star A, right? By definition, plus 2 epsilon. Because mu star A is mu of A by this property. Okay. Okay, so and epsilon can be arbitrary. So which tell you that mu of A is equal to mu star A. So combine the least one and the previous least one. So you give me that the mu star A equals to mu A. Okay. Yeah, I just figure out that yeah. So my definition for A be my definition for regular yeah. So I should say that there is this F is closed and it belongs to the elementary set, right? And the G is open belongs to elementary set. Okay, so this is the key idea that I miss this condition. So that's why in these directions I can say that the F is elementary, because I only define the mu act on elementary set, but for outer measure you can define on arbitrary set. Okay, so now let's prove the second say that if E is a union of En, then the outer measure of E should also equal to the summation. And this one yeah, this one is also simple. Okay, so this is a common idea. Let's say E is a union of En, and let's assume that mu of En is less or infinity. Right? Otherwise, that E will be infinity. Right? You can prove by definition. Right? So for n, so let's say given epsilon greater than 0, right? Due to the inf, I can find a covering. I can find A and K, which cover An. Right? So for each n, sorry, for each K, which we cover En. That means for each mu A and K, right? So K from 1 to infinity will less or equal to mu star En by the property of inf, right? En plus epsilon divided by 2 to n, right? So this is the old technique, right? Because you can use the geometry series. Okay. So now mu star E will less or equal to, right, by the property of infiniment, right? So E is covered by everything, right? So mu star will less or equal to sum of these. Summation n from 1 to infinity, K from 1 to infinity, mu An. Less or equal to summation n from 1 to infinity, K from 1 to infinity, mu star En plus epsilon 2 to n. Sorry, there's a note here. Okay, so that means this guy is summation n from 1 to infinity mu star en. And then now this is geometry series, right? Epsilon. So epsilon can be arbitrary. Epsilon can be arbitrary. So that means mu star e is equal to summation n from 1 to infinity mu star en. So this is the subactivity. Okay, so now we have all the tools. We can start to prove the main theory. Okay. So let me just write down the two important definitions. Right. So let's say A belongs to a set of RP and B belongs to a set of RP. Then I can define the first one is SAB, defined to be A minus B union B minus A. Okay, so this is just this is A, this is B, these are S. Okay, so also called this is called the symmetric difference. Okay, now I can define B defined to be DAB, defined to be the mu star, right? So I can define outer measure of SAB. Okay, and I write, let's say I write a set AN to A if D ANA. So ANA goes to 0, okay, as a outer measure. Okay, so this is the definition. Okay, so now I can introduce my notation, which is very hard to understand what's going on. Okay, so definition. If there is a sequence, if there is an AN go to A, so now each AN belongs to an elementary set. If there's an AN belongs to an elementary set and AN goes to A in terms of this, then we said A is finitely mu measure. A is finitely mu measure. I should say finitely mu measurable. Okay, and I can write A belongs to this. Okay, so this means that, let me just speak a definition again. So the mu need to satisfy the 4 properties, and suppose that there exists an elementary set A and such that AN approach to A in terms of this outer measure case. So given the mu, you can deconstruct outer measure, and suppose there exists an elementary set such that an approach to A, then we say A is finitely mu measurable, and A. So my notation is that MF mu means that this definition. Okay, so that means we can use your elementary school idea that if you want to compute something irregular, then you put all the intervals in it, and you try to make this interval smaller. So this is just the mathematical definition. And the B, you can define A. You can define so if A is a union, so this is a union of countable collection of finitely mu measurable set, and we call A is mu measurable. A is mu measurable. Okay, so that means A is mu measurable means that A is a collection of union of finitely mu measurable. So now I write A in terms of mu. Okay. Oh, okay. Yeah, this is definition. Okay, so main theorem. Finally, okay. So this finite, this mu measurable set, right? Basically, this is your, I mean, maybe this is the second time, not the first time you heard about Lebesgue measure theory. So this all the set which are Lebesgue measurable forms a sigma ring. So this is the key idea. Theorem, mu over is a sigma ring. And this mu star outer measure is countably additive. So this is the theorem, and the proof is maybe very long. Okay. Yeah. So let me just develop. Let me just give it a proof, and after we finish this proof and this video, if we finish this video, with the proof is it's a very long. So maybe if you are interested, you can just keep watching and maybe speed up. Okay. Maybe speed up quick. Okay, so let me just see the simple lemma, which is important. So first one is that SAB, right? Symmetric difference is the same as SBA. So yeah, this is trivial, right? Because SAB equals to A minus B union B minus A. Okay. And the second is that SAA is trivial, right? And the third is that SAB is less than SAC union SCB. Okay, so this is you can draw a stupid diagram ABC, and you can see what this is SAB. Which is less than SAC, right? Because I mean you can draw this is also trivial, right? Because SAC is maybe here. Sorry, what the hell is going on, right? So this is, let me just draw a picture. This is SAC, and then this is SCB. Right? So you will recover this part. You will add more this part. You will add this part. Okay. And so these three are trivial, and number 4 is also trivial. So I don't want to prove, but you can prove by yourself. So basically, S1 A1 union A2, B1 union B2, and also A1 intersection A2, B1 intersection B2, and also A1 minus A2, and B1 minus B2 is less than SA1 B1 union SA2 B2. And these are trivial. I mean, you can you can prove by yourself. Okay, so combine these, we get the first one is DAB, which is DBA, and then we get a DAB, which is less or equal to DAC, right? By definition, and DBC. Okay, the reason is that the mu star is a definition. My mu star definition is that E1 less than E2, then mu star of the E1 is less or equal to mu star E2. Okay, and also this, if you take D, you get DA1 union A2, B1 union B2 is less than DA1 B1 DA2 B2. Okay. Okay. Yeah, that's it. So this is the simple lemma. Okay, so now let me just write down another property which is important. Okay, so another final one, the final property. Okay, so final property is that the mu star A minus mu star B, so given into set, will less or equal to DAB. Okay, so the proof is that I mean, if both are infinite, this is not important. So let's suppose that one of is finite. So suppose one of is finite. Let's say one of mu star A is finite. Let's say mu star B is finite. Okay, and suppose 0 mu star. Okay, so this is just suppose, right? I suppose mu star B is finite and the mu star A greater than equal to mu star B. If the proof is not the same, I mean you can just exchange A and B. Sorry, this is not important. Okay, so all you need to know, all you know, right, by this, then you can easily say that you're. Oh, by the way, the simple properties I forgot to mention is that the dA empty is the mu star A. Okay, so dA empty, that's equal to DAB plus DB empty, which tell you that the mu star A, that's equal to DAB plus mu star B. Okay, and then just minus B and take absolute value. That's it. Okay, so now it looks like what this D is like the metric space, right? But the difference is that if DAB is 0, you definitely do not have B equals to A. Okay, but you can define A the same as B if DAB is 0. This is equivalent class. Okay, but by this lemma, we can easily get this, right? So we have the following. let's say A is a finitely mu measure, and B is a finitely mu measure, and right. So by definition, I can find A and approach A, B and approach B, such that D A N A goes to 0, and the D B N B goes to 0. Right, by these two, then we can get the following. Or you can get AN union BN approach to A union B, and then AN intersection BN approach to A union B. So AN minus BN approach to A minus B, and mu star AN goes to mu A. I think this is I proved in the first video, right? So these are all trivial, right? Because we have the property of this DAB, right? So your DAN and BAN were bounded by DAB. I mean, you do the same, you do the previous, you do this previous work, right? You just do this, right? I mean, right, and you can use this and this, right, and this, basically. Okay, maybe I think this is trivial. Let me see whether I should give one example to make you happy. Let's see. Okay, maybe let's prove the first one. Yeah, I think this is just using the previous lemma, but let me just give the first one. So AN union BN approach A union B, and then we want to prove. I mean, this is true, right? So basically follow the right. See what we should do. So right. So I mean we can just using right. So we want to prove that this approach to A union B. So we want to argue this, right? We want to argue that this guy goes to 0, right? But by lemma that I just showed, this is less than these two, right? So DANA plus DBNB. So these two approach to 0 as n goes to infinity. So these two goes to 0. And this is first one. And this one you do the same thing, right? And this one, I mean, just using the lemma. And for D and minus Bn, you use this lemma. Okay, you can easily prove it. Okay. Also, yeah. So from these two, from this we know the union is okay, right? And difference is okay. Okay. So which prove what? Which prove that this guy, this finitely mu measurable set is a sigma ring. It's a sigma ring, right? Due to these properties. Okay. And also, okay, so now I want to prove it's not just sigma ring. We want to prove it's mu star is additive, right? Because I think we only prove let's see 0, right? So we already arrived that when this is finite, then this is a sigma ring, and then let me just prove it's additive. Okay. Okay, so the remaining is to show mu star is additive. So what it mean by additive? So this means that the mu star A union B is a mu star A plus mu star B if A union B is trivial. Okay, so we do the same thing, right? So remember that in my previous video, I proved this by the property of the measure, which mu star AN which mu star AN plus mu star BN is mu star AN union BN, sorry, intersection BN and the mu AN union BN. Okay, so as n goes to infinity, right, and by the definition, as let's say that n goes to infinity, so this mu star AN approach to mu star A, right, by my properties, and mu star B plus mu star A union B and a mu star A intersection with B. Right, so if A union B is 0, then by definition, your A star A intersection B is 0. Right, so you get this. Okay, so this is this definition and also using my previous theorem. Okay, so which tell you that mu star is additive on a finitely mu measurable set. Okay, so the final is to bypass this. So the final is to bypass these two properties. The first is that what sigma ring property, and the second is that additive. Right, so we want to prove this. We want to bypass these two properties from this is very hard to write. Finitely measure mu set to countable union of finitely measurable mu set. Okay. Okay. So proof. Okay. So this is very let's see. So we know that say A belongs to this finitely and not finitely just the mu measurable. Then A could be represented countable disjoint subset. Right? So A can be represented countable disjoint. Let's say if A is A prime, let's say A prime belongs to countably this F mu, and I can try to write this A prime to the disjoint union. Okay, so reason the techniques looks like this, right? You can write A into A1 prime up to union up to A prime minus A prime union of A prime, A minus 1 prime. So it's n from 2 to 3, 4. Okay, and then you can easily check that A is a union of AN, and each AN is disjoint. Okay, so by the property of mu star. So remember that mu star now is additive. Okay. So let me just so by this, right? I mean you can use a definition, right? So definitions tell you that mu star A less or equal to summation mu star AN and from 1 to infinity. Also, and on the other, so this is the first directions, right? On the other hand, since A looks like this, so A is greater than A1 union A2 up to AN. Okay, and we have this additive, so tell you that the mu star A is greater or equal to mu star A1. Sorry, mu star. Oh, sorry, this is definition, right? So mu star of A1 union A2 up to AN. This is the definition of the outer measure, and then you use the additivity, so which is greater than equal to summation of mu star AI, I from 1 to n. Right, so you can take n to be infinity, the mu star A greater or equal to summation of infinity. So which you prove that mu star A equals to summation mu star AN. Okay. Okay. So let's see. So we have this. Okay, so now let's say mu star A is finite. So suppose mu star A is finite, and you define Bn to be A1 union A2 up to An. And basically your original, then you got dBn, right? dBn is a dA union of An, right? So basically mu star AI, I from 1 n to infinity is a summation of mu star AI, since there are disjoint approach to 0 as n goes to infinity, right? Suppose this guy converge, so partial sum goes to 0. Okay, so which tell you that what Bn converge to A, right? In my notation. Okay, so that means what? Bn is what? Bn is belongs to this finitely mu measurable. Okay, so which tell you that A belongs to finitely mu measurable. Okay, so what we have shown is that A belongs to finitely measurable mu measurable if A is a measurable mu set and mu star A is less than infinity. This is what we just showed. Okay. Okay, so but we haven't not done, we have not yet done, right? We need to prove we need to drop this condition. Okay. Okay. So yeah, so let me just okay. Okay. So now finally we want to drop this condition, right? I mean I want to drop this condition. Okay, so now finally I can claim mu star is countably additive. So this is what I originally want to prove, right? I want to prove it's countably additive on this. If it's finite, then it's trivial, right? Let's suppose we don't do the finite, right? So let's say A is a union of AN such that AN is a disjointed, and each AN just belongs to this. Okay, so now if AN is infinite, if AN is infinite, right, then property of outer measure will give you A infinite. So it's not important. And we already showed that this mu star, if mu star AN is finite, then by the previous step it becomes this, right? Right. So I mean, if mu star AN is finite, then AN belongs to the AN will be finite. AN will be finite one, right? So if mu star A is finite, then the finite of the finitely mu measurable and the mu measurable are actually the same. So which proves that if AN is if every AN is finite, right? So if every AN is finite, then basically you can just take the results, right? You can just use the property of this. You can just use the property of the countable additive on the finitely measure. So which prove that mu is countably. Which prove that the mu star is countably additive. On this. Okay, so we prove it's countably additive. Now we need to prove what? We need to prove that this is sigma ring. Okay. So finally, we want to show that this is a sigma. So if it's finite, then it's proving sigma ring is trivial, right? You just use the previous lemma. Okay, so let's say if AN belongs to this one. Let's say any 1, 2, 3. Okay, suppose this is this. And by the previous results that this AN, so sorry, by the definition, this a union of these will become this. Okay, this is trivial, right? Because countable of unions is countable of union, countable union will still give a countable, right? So it's trivial, right? Because the countable, so right now each AN is a union of finitely mu measure, right? So the countable union of these, so each AN is a finitely countable, finitely. Sorry, let me see the definition. Right, so each of AN is countable union of finitely mu measure. So the countable union is still countable, right? So countable. Trivial. Okay. So the union is trivial. So final is what? Difference. Let's say A belongs to the finitely measure mu, and sorry, mu measure, and B belongs to mu measure. So that means A is this. B is this. And you can easily show that AN intersection B is a union of AN with BI, I from 1 to infinity. Oh, well, by the way, this AN and BN are finitely measured, right? So are finitely mu measured. Okay, and you can easily do this. Okay, so this is finitely mu measure. This is finitely mu measure, right? So this is finitely mu. Sorry, this is finitely. So this is mu measurable. Okay. Okay, and since now mu star AN union B is less or equal to mu star AN, right? So mu star AN is finite mu measurable, so it's less than infinity. So which tell you that an intersection B belongs to finitely mu measure. Okay. So an, so it means this means an minus B belongs to finitely mu measure. Sorry for my bad notation. So finitely mu measure union is mu measure, right? Because so right, so this A minus B will be union of, I mean, the A minus B can be written as a union of n from 1 to infinity, an minus B. And your results tell you this, right? Because, I mean, this is because you can just use an minus this. Okay, so prove that, so use this union, A minus B equals to an minus B union, which tell you that A minus B becomes so A minus B is a collection of the countable finite mu measurable, right? So it is mu measurable. So A minus B belongs to this. So that means this mu measurable set is a sigma ring. Okay, so final notation. So that means we prove our theorem, and the final notation is that we replace mu star A by mu of A. If so, now I can replace this by if A belongs to finite mu measurable set. Okay, so we use outer measure as our definition when we try to start from the measure on regular elementary set and extend. So that means we finish our extend property. So now we have a lot of set which can be measurable, and outer measure will define to be its measure. Okay, so we use outer measure as a measure to extend elementary set and call measure. Okay, so definition for original regular, let's say for m. So now I can define a mu to be m, right? So if mu to be m, this m of I to be this bi minus ai for each elementary set as a box, the product of box. Now, so this outer measure is defined to be the back measure. Okay, so this is the exactly what I said, the construction of the back measure. Hardcore definition. Okay, so this is the definition of the back measure, and this is whole process. So basically, we start from an elementary set, and we prove that if you use the outer measure to extend it, so finite cover, I mean, you countable cover, and you take the infiniment, then it will give you the volume. I mean, this is very, very intuitive, right? Because you can just cover like your elementary school, if you want to compute the volume of an irregular shape, and you will put the finite, you will put some finite, I mean, finite box, right? So for example, if you want to compute, let's say, irregular shape, then you will put a box and count the volume of a box, right? And then try to make this box smaller. But mathematically, you need to prove this is a sigma ring such that the collection of all these things is somehow good behavior, such that the A minus B exists, A union B exists. So it should give you all the properties of what you have in mind is volume, right? So volumes, I mean, in terms of the back measure, is so non-trivial that you need to go through every proof and define all what's regular, what the hell is going on, and give all the proof of this. See you guys next video. So next video, I will define so-called measurable function, and next we take some standard like a step function, the LDCT, Fartok's lemma, and I will finish the routing. Bye bye.